Hello everyone. Welcome back to another exciting session. Let's start with a simple question. If you and your friends want to form a doubles tennis team from 3 players, say X, Y, and Z, how many possible teams can you make? If you pick X and Y, that's the same team as Y and X. Unlike arranging books or letters, the order doesn't matter here. Pause. And that's the essence of combinations, when we only care about which objects are chosen, not the sequence. So whenever we are talking about committees, groups of friends, handshakes, or chords in a circle, we are in the world of combinations. Now, you might be thinking, how does this connect with permutations? Let's see. Every combination of our objects can be arranged among themselves in our factorial different ways. That means NPR equals NC are multiplied by R factorial. Or, equivalently, NCR equals NP are divided by R factorial. So permutations are always bigger in number because they treat every different arrangement as unique. Combinations collapse all those arrangements into one selection. It's like saying, I don't care in which order you entered the party, I only care about who showed up. Now let's write the general formula. If we want to choose our objects from n distinct objects without regard to order, then NCR equals n factorial divided by R factorial multiplied by bracket n minus R factorial. This formula works for all r between 0 and n. By definition, NC0 equals 1 because there's exactly one way to choose nothing. Similarly, NCN equals 1 because there's only one way to choose all. Another important property, symmetry. NCR equals NC of n minus r, that means selecting our objects is the same as rejecting n minus r objects. Beautiful symmetry in action. Let's confirm this with a simple case. Suppose we have 4 objects A, B, C, D. How many ways can we choose 2 at a time? If we list AB, AC, AD, BC, BD, and CD, that's 6 total groups. Now check with the formula. 4C2 equals 4 factorial divided by 2 factorial times 2 factorial. That's 24 divided by 4 equals 6. Perfect match. If you visualize these 4 points as dots on a circle, you can see exactly 6 chords connecting them. That's combinations at work. Combinations also come with some very handy properties. First, symmetry. NCR equals NC of n minus r. For example, 10C3 equals 10C7. Second, recursion. NCR plus NC of a minus 1 equals n plus 1CR. This is what generates Pascal's triangle, one of the most beautiful patterns in mathematics. Third, special cases. NC1 equals n and NC2 equals n times n minus 1 divided by 2. These properties aren't just elegant, they're extremely useful shortcuts for exam problems. Now let's solve a slightly more complex problem. Suppose we have 2 men and 3 women. We want to form a 3-member committee. First, total number of ways, 5C3, which equals 10. Now, let's set a restriction. The committee must have exactly 1 man and 2 women. Choose 1 man, to C1, which equals 2. Choose 2 women, 3C2, which equals 3. Multiply them, 2 times 3 equals 6. So, out of 10 total committees, 6 will have exactly 1 man and 2 women. This case-by-case style of solving is very common in competitive exams. Let's see how combinations sneak into daily life and games. 12 people in a room, how many handshakes are possible? That's 12C2 equals 66. Playing cards, the number of ways to choose 4 cards from a deck of 52 is 52C4, which equals to 70,725. Geometry, number of chords formed by joining 7 points on a circle is 7c2, which equals 21. So from handshakes to poker, from geometry to team selections, combinations are everywhere. So let's close the chapter. A combination is simply a selection where order does not matter. The formula, NCR, equals n factorial divided by r factorial times bracket n minus r factorial. Key properties: symmetry, recursion, and boundary cases. Applications: committees, teams, handshakes, cards, chords, and more. The golden distinction: use permutations when the order matters, use combinations when it doesn't. And that, my friends, is the essence of combinations. In the next session, we'll see how permutations and combinations come together beautifully in the binomial theorem and in probability. Stay tuned, it only gets more exciting from here.